to the PCA again. So maybe we go back to the formula. Yes. So what we first do is we calculate the covariance matrix. And then, I mean, we have to solve this eigenvalue equation for the covariance matrix S. Then we get the eigenvalues, lambda m. And the eigenvalues, the size of the eigenvalues, I mean, these eigenvalues, they're all positive, and the size of these eigenvalues gives us the variance in the direction of the respective eigenvector. Yeah? So the spectrum of the eigenvalues is quite interesting when, for our data set, we solve the eigenvalue equation. So we see that the principal component, I mean, that's the definition of the principal component, has the largest eigenvalue. But here we see there is quite a big difference between the largest eigenvalue and the next ones. Okay, and I gave you these LexMate data as the exercise, and then in the exercises session last week, some students showed me nice pictures. What they did is they projected the data onto the two largest eigenvalues, because this can be easily visualized on the screen. Yeah? And now if we do this with the raw LexMate data, the not normalized LexMate data, then we get this plot. Yeah? And I mean, the reason is, I mean, here you don't see much structure. It looks like an almost random distribution of points. But the reason is quite simple. The reason is, in the not normalized LexMate data, here you see the data. If you don't normalize these data, then of course the leukocyte value is by far the largest value, and therefore the variance will dominate all the other variances extremely. And then there is this the h, which is the next value with a large variance, because the h varies between something like 3 and 90 years. Huh? So the variance of the h also is quite large. I mean, even though these values are bigger, because I mean these are the fever values without the decimal point, but the variance is quite small because it's values between 360 and 400. Huh? So the variance is around 40 here. No, it's even smaller. The variance would be around 20, but here the variance is something like 60. Huh? Okay, and that's why, I mean, so we could already know in advance that the principal component would more or less be the leukocyte value. Yeah? And that's actually what happens. If you look at, here we have, sorry, it's cut on the slide. The principal component, which is this here, sorry, you can't see it, behind here we have a value of something like 10,000 compared to these extremely small values. Huh? So the principal component just projects you out the leukocyte value. And the second principal component, you see, has a value of 100 here and very small values here. And back there, the two fever values, they are also a little bit bigger than the others. So it's a combination of age and the fever values. And that's why we get such a picture without structure. But if we look at the normalized values, and that's what I saw when you showed it me, that's the picture you get when you project, when you normalize your data, calculate the eigenvectors of the covariance matrix, and project on the two largest eigenvectors. That's the picture you get. Highly structured. And now let me ask the question, what does this structure tell us? I mean, or let me ask, what can you see here? I mean, it's just about pattern matching, nothing about PCA. If I would ask a 10-year-old kid, it would immediately give me an answer. Isn't this right part a copy of the left part? At least it's very similar. Look at this bunch here. It's almost exactly a copy of this, and this is copied here, and so on. And where does this come from? Now look at this axis. Here we have 0, and here we have 1. Now what's the reason for this almost identical copy? The reason is that many of our variables are binary. So our data points, there is, I mean, each one of the binary variables here, take this variable here. I mean, a part of the data points have the value 1 here, and the others have the value 0. So this binary variable splits up our data in one set with the value 0 and another set with the value 1. And now if this variable is not really very significant in splitting up our data, maybe it's not really relevant. So it's just, I have the data and half of them have the value 1 and the other half have the value 0. And this then leads to an almost identical copy. I mean, this is the part of the data with the value 0, and this is the part of the data with the value 1. And I guess an explanation for this structure in here would be similar. But here we would have to look closer. I mean, we now could do the same thing and just use one of the binary variables and neglect all the others. Okay, so you see PCA is a nice tool for data analysis. Okay, so much about PCA. And now we come into the next section. We now go into we will have this semester this statistics chapter, and then we will have a continuation of the function approximation chapter. And we are still in the statistics chapter, but this is kind of the overlap between statistics and function approximation. We will now go into the statistical approach to function approximation, which is, I mean, this will give us powerful techniques for function approximation, first, and second, it will lead to a much better understanding of what's going on. So we will see, for example, problems with overfitting, but we will also see how we can solve them. And the magic formula is Bayesian regression. So we will use Bayesian statistics, more or less based on the Bayes formula, and we will see, we will learn a lot about function approximation. But because it's a statistical method, we have to go a little bit into statistics. Okay, so now we first talk a little bit about estimators and their properties. Now here we talk about an estimator T gamma, which is used to estimate some unknown parameter gamma. I mean, we may want to estimate the expected value, for example, of a distribution, or the variance, or some other quantity. Okay, so the estimator is a function that maps our sample x onto a set of, this is the sample space. It maps from the sample space onto the parameter space. So one particular sample is a set of data points, x1 through xn. Okay, and now it's important, such an estimator has two desirable properties. And the first one, which is really very important, we want our estimators to be unbiased. And unbiased means that the expected value of the estimator gives us the exact value of the parameter. I mean, look, we are calculating the estimator itself from a finite sample set. And this, of course, only gives us an estimation of our parameter. That's why it's called an estimator. And the question is this estimation good or not? And the first property is unbiasedness. And this means that the expected value of the estimator has to be the correct parameter value. The expected value is nothing but the limit for n towards infinity. So if we increase the size of our sample set and let n go to infinity, then the limit has to be gamma. Okay, yes, and also of course, if we take a finite sample set, we would like to have, even for infinite sample set, we want the variance of our estimator to be as small as possible. So such an estimator, T gamma star, has minimum variance if the variance of this estimator for the parameter gamma is less than or equal to the variance of any other estimator, of any other unbiased estimator. Of course, I mean, from this point on we talk about unbiased estimators, and then we can ask how large is the variance of it. Okay, now let's look at particular examples of estimators. The first and most important is the sample mean. You all know it. And the sample mean is an estimator for the expected value. The sample variance, what we have here, is an estimator for the variance. And yes, quite often people ask, why do we have the 1 over n minus 1 here and not like here the 1 over n? Because this is nothing but averaging over n sample points. And why don't we then normalize this sum with the factor 1 over n? And the reason is here exactly because if we take 1 over n, then it's a biased estimator. It's only unbiased if we use this normalization. And this is one of your exercises to prove that this is an unbiased estimator. Okay, now let's look at this estimation task. Oh yes, and let me mention, these slides are from Markus Schneider. Markus Schneider was one of the scientists in my group until about 2 years ago, yeah, I guess. He prepared this part of the lecture, which was actually an excellent job from him. And now I am happy to use his slides for this lecture. And I mean, he is a researcher. He started doing his master thesis in this area, and we will actually see in maybe 2 weeks the results of his master thesis, where he used Gaussian processes. Okay, yeah, and now here, this is not about Gaussian processes, but about Gaussian distributions. Okay, so what we do here is, we sample from a Gaussian distribution. This green graph here is a normal distribution with a mean of 5 and a variance of 2. So this is the mean 5, and here you see the width. Yeah? And we sample data points from this distribution. And now here in this first example, we just take 2 samples. These are the blue dots here. We take these 2 samples. And now, now we take the statistics view. Now suppose we don't know this original underlying green distribution. We just know these 2 data points. And now our task is to estimate the shape of this density function. We don't know where these data points come from, but we now estimate, what does estimation mean? We estimate the mean and the variance. And here you see, it's not difficult estimating such a normal distribution. What you need to know is the mean and the variance. And what do? You calculate the sample mean, and the sample mean is exactly here in the middle. And that's why the center of this black curve is exactly in the middle between these 2 data points. And then you calculate the sample variance, and now you plot this black curve. So this is now our estimated density, and of course it's not surprising that from 2 data points we don't get a perfect estimate. Now if we take more data points, like 20 samples now, distributed like that, again 20 random independently drawn samples from the green density function, and now we calculate mean and standard deviation, and we get this new black density, which is already quite close to the original density function. And if we take even more samples, if we take 1,000 samples, then you see we get a very good estimation. And that's because we use unbiased estimators. Okay, so I mean, you have seen that it's actually trivial to estimate a normal distribution. Okay, yeah. Oh, yeah, and here we have a proof of the unbiasedness of the sample mean. And what do we have to show? We have to show that the expected value of the mean is equal, or the expected value of the sample mean is equal to the mean of the underlying distribution. So we calculate the expected value of the mean, and now then, I mean, we can pull this expected value into the sum, because the expected value of a sum is the sum of the expected values, because of the linearity of the expected value. Now we pull this expected value in here, and now what is the expected value of all our variables xj? It's of course mu. So we have 1 over n times the sum j equal 1 to n of mu, and you see this is then constant. We can pull it out, and then this gives us mu. So this proof is very easy. Now let's prove the unbiasedness of the sample variance. Yeah, in order to prove this, we need to know this property. So we can write the sample variance. This is the sample variance. We can write the sample variance in this form. I mean, this part up to here, this left part here, this looks quite like the sample variance, but if it were the sample variance, this wouldn't be mu, it would be x bar. Because when you estimate the variance from the sample, you don't know the mean of the underlying distribution. So the only thing you can do is you calculate the sample mean. So this would be x bar. But you can write the sample variance in this way. Look, here appears the x bar. Okay, and this part of the proof is your exercise. You have to show that this formula is identical to the sample variance. Okay, so yeah, now we can calculate the expected value of the sample variance, and now this is the expected value, of course, of this formula. So we can again draw the expected value into these sums, so into this sum and here. And yeah, now look, what do we have here? The expected value of xj minus mu squared. And this is nothing but the variance of xj. And here we have the expected value of this other variable, which is x bar minus mu, and this is nothing but the variance of x bar. So this is the variance of the sample mean. Yeah, and now let's look at this. Yeah, of course, here we see that, so what do we see? Yeah, I mean this is, this is constant. The variance of xj is the same for all our variables xj. Because these variables, we assume that we draw them independently from an identical distribution. So then, of course, the variance for all these variables is the same. And, I mean, we can just take this constant value of the variance, which is sigma squared, and we get n times sigma squared. That's what we get here. And now here we have the variance of the mean, and we already know from the central limit theorem that the variance of the mean is sigma squared over n. Okay, yeah, and now we are basically finished. Why are we finished? Because for n towards infinity, this term goes to 0. Look, this n cancels out, and then we have sigma squared divided by n minus 1. For n towards infinity, this goes to 0. But this, of course, does not go to 0. Yeah. And you see, I mean, what is the limit of this? This goes to 1 for n towards infinity, and so the limit is sigma squared. And now we have proven that for n towards infinity, the sample variance converges to the variance of the distribution. Any questions? Okay. Yeah, okay, and I mean, we don't prove this here. The variance of the mean is, I mean, that's what we already know from the central limit theorem, and this is the variance of the sample variance. So how does the sample variance vary? And it goes proportional to sigma to the 4th power. Okay, some more nice formulas about expectations and covariances, and I think we will need all these formulas. I mean, this is basically the definition of the expected value of some function of our variable x. And that's how it's defined. I mean, it's the integral over the density times our function over the variable x. Okay, and here we have the definition of the variance of some function of x. Not the variance of x, but some function of x. I mean, we have seen examples right before. I mean, one function of our variable is the mean, for example. Okay, so the expected value of some function is the expected value of f of x minus the expected value of f of x, and this difference squared. And now it's easy to show that this is equal to the variance of f squared, is equal to the expected value of f squared minus the expected value of f squared. That's easy to show. And the covariance of two variables x and y is defined, I mean, maybe we should compare the variance and the covariance again. Because, I mean, they are quite similar. Let's look at this first. This is the expected value of x minus e of x times y minus e of y. So this is the difference between our variable and the expected value. So this tells us, for example, so if this is the x-axis, and here we have e of x, the expected value. And now suppose suppose we take one value x, which is here, and x is smaller than the expected value, so then x minus the expected value is negative. And now if we look at the axis for y, and here we have e of y, and suppose y also is smaller than the expected value, then we see that for these two samples, here we have a negative difference, and here we have a negative difference. So the difference goes in the same direction, in negative direction. So we have then the product of two negative values, which is positive. And this means the two variables are correlated. The difference from the expected value goes in the same direction. If they both go in positive direction, the product also is positive. But now suppose it's different. X has a negative distance and y a positive distance. Then I have a positive value times a negative value, and I get something negative. And such a negative term here is, we call it an anticorrelation. Okay, but now look, we have the expected value of this product. And now suppose we take 2 times the same variable, x, and then we get the expected value of x minus e of x times x minus e of x. And so you see we get this here. So the covariance of a variable with itself is the variance of the variable. And here we have a similar formula to this up here, which is the covariance of x and y is the expected value of the product x times y minus the product of the two expected values. Yes. So suppose our two variables x and y are uncorrelated. Uncorrelated means the covariance is equal to 0. And then you see these two values have to be the same. So this means the expected value of the product of the two variables is equal to the product of the expected values. So yeah, please remember this, we will need it quite soon. Okay. Yeah. Oh yeah, and here we actually prove it. Yeah. Now, if our variables are independent, then the probability for observing x and y decomposes into the product of the two densities. Yeah? I mean, that's the definition of independence. And now we calculate the expected value of the product of these two guys, which is the integral of the density times x times y, and of course integrated over x and y because it depends on two variables. Yeah. And now here in this step we now apply our independence. So we replace this by the product P of x times P of y. And now you see that, of course, P of x only depends on x. This only depends on y. And so we can split up the integral into two integrals. Into this first integral over y and the second integral over x. And if you look at this, you see this is the expected value of y. And this is the expected value of x. So it results in e of x times e of y. And we are finished. And yeah, again, we see that for independent variables, we get a covariance of 0. Okay, yeah. Now let's look at Gaussian distributions. I mean, Gaussian distributions will be very important in this whole chapter. We already looked at the Gaussian distribution for the one-dimensional case, but now we will need Gaussian distributions in higher dimensions. And now we will look at a few basic facts about Gaussian distributions, and then we will apply them. And finally, in the last part, which is about Gaussian processes, we will even go to Gaussian distributions of infinite dimensionality. So first we have a one-dimensional Gaussian distribution, then we have multi-dimensional, higher dimensional Gaussian distributions, and at the end we will learn about infinite dimensional Gaussian processes. But let's do it slower. Okay, this is a nice picture of such a Gaussian distribution, two-dimensional. And here we have the definition. Okay, so a Gaussian distribution is specified by a mean vector now, of course. It's higher dimensional, so the mean is a vector. And the standard deviation or the variance is no longer one value. It is now the covariance matrix. So we have the mean vector mu and the covariance matrix sigma, and now this is the formula for the density function, and it's actually quite similar to what we had in the one-dimensional case. In one dimension, for example, here we had the square root of 2 pi, and here we have 2 pi to the power d half, and d is the dimension of our space. Okay, and here we have the determinant of the covariance matrix, where we had before just the standard deviation sigma. Yeah, it's the square root of the covariance matrix. And in one dimensions, the square root of the determinant of the covariance matrix, and in one dimension this would exactly be the standard deviation sigma. And now comes the important exponent. Now in the exponent we do have, of course, our vector x, and you already see that, I mean, if we would multiply this vector with with a scalar standard deviation, this would give us problems, because, I mean, this is the exponential function, and this can only be applied to scalars, not to vectors. So the result of this whole formula here has to be a scalar. And that's how we typically elegantly get a scalar out of a matrix and a vector. So you multiply this matrix from the left with the transpose of the vector and from the right with the vector, and you end up with a scalar. Yeah, and also it's very important to see this is not the covariance matrix, it's the inverse of the covariance matrix. Maybe we should write down the one-dimensional case. So n of mu comma sigma squared is equal to 1 over square root of 2 pi times sigma times e power minus x minus mu divided by sigma squared. Yeah, that's the one-dimensional formula. And you see, we have this sigma squared in the denominator. And I mean, our covariance matrix, let's look at it in, let's say, 2 dimensions. Then here we get sigma x squared, and here we get sigma y squared. And I mean, here we get the two values, the covariance. So here we get the covariance of x and y, and here we get the covariance of y and x. And since the covariance matrix covariance is symmetric, this matrix is symmetric. Okay, and for the case of 1 dimensions, what remains is this. And the inverse of this scalar matrix is this. Okay, so what we have to use is the inverse of the covariance matrix, and we multiply it from the right with this column vector, x minus mu, which corresponds to this here. And from the left with x minus mu transpose. And then, we forgot this 1/2 here. Yeah. This is very important. And maybe, yes, I mean, please do as an exercise, look at this. I mean, this is written in vector notation. But now if you write down this in component notation, so if you want to know the ith component of the exponent, how does this look like? It also gets a nice form, and then you will, oh yes, I mean, why don't you help me? I forgot a square, of course, here. Here we have a square. You see, I mean, this square corresponds to the product of this guy with this. And if you write down this whole thing in component notation, you will find the squares of the individual components of these vectors. And I mean, at this point, it's very important that you get exercise with all these formulas. Otherwise, you will get lost quite soon. Okay, so this is the formula for a function shaped like that. And we will, of course, now look at examples and details. But before we look at the examples, let me note that I mean, here we have mu, and here we have sigma. And mu and sigma are the mean and the covariance matrix of this multidimensional distribution. But be careful, it has to be proven that this parameter mu here is the mean. I mean, mu is, this mu here is the expected value. I mean, we are not talking about samples. Now here we talk about the distribution, and mu is the expected value, and sigma is the covariance matrix. So this has to be replaced by expected value. And this has to be proven. And how will this be proven? And actually it will be an exercise for you to prove that the expected value of such a normal distribution is mu. How will this be proven? You will just apply the definition. Let's go back. Here. You will take this formula. You will take this formula and replace this f of x by the normal distribution. And then you will solve this integral. And you will see that it is mu. And the same holds for the covariance. Oh yeah, okay, and here we have another remark. If the variables x1 through xd are all independent, then sigma is a diagonal matrix. Yeah. Why is this the case? We have just talked about independence.
Because the covariance is 0?
Yeah. Because the covariance of all pairs of variables is 0, but what is not 0? Yeah, the diagonal elements. And what are the diagonal elements of the covariance matrix? They are the variances of the individual variables. So the diagonal elements are the variances of x1 through xd. And now this is important. Look, the covariance matrix for our variables x1 through xd. So that now this is the covariance matrix. In the diagonal case, we get the variance of x1 down to the variance of xd. And the rest is all 0. Yeah. And this is a very nice case for our normal distribution. Now suppose this sigma here and here is diagonal. Huh? What is the determinant of a diagonal matrix? It's a product of all the diagonal elements. And now you see something very nice. It's a product of all these guys. And this determinant appears in the denominator. Now, what is your first question when you see a denominator as a mathematician? It can be 0, yes. Now, can this be 0, this product? Yes, it can. When can it be 0?
If one variance is 0?
Yeah, if one of the variances is 0, then we are having a problem with our normal distribution. Now, what does that mean? Let's go back to this nice image here of such a Gaussian distribution. Oh, this is not so nice an image for the case of a diagonal covariance matrix, because here the covariance matrix is not diagonal. So if this is x and this is y, then here the covariance matrix is not diagonal. Let's look at such examples. No, let's go on. to this, yeah. Here we have, look, here we have examples of Gaussian distributions, all with diagonal covariance matrix. The expected value is 0 in all these three examples. And now look, with this covariance matrix, 1, 1, 0, 0, the density function looks like that. Yeah? Now, with 0.5 here, it is more narrow, but a little bit higher. And with 2, we have a larger variance, it looks like that. And now my question is, how would it look like? Let's take this one. And let's make this variance to 0. How would it now look?
Like the one-dimensional case? Something.
Yeah, something like the one-dimensional case. I mean, it would be if this second variance would be 0 and this is the y direction, then it would be extremely flat. Yeah? The width would actually be 0. But that would mean the height would go to infinity because the whole two-dimensional integral over this density function has to be 1. It has to be normalized. The sum of all probability density has to be 1. So it would be infinitely high. And that's why this is mathematically not tractable. So this limit for for width 0, for variance 0, is not allowed. Yeah? And that's what we see here. That's why it's not allowed. And the next point is, take this diagonal matrix and make one element in the diagonal equal to 0, then this matrix becomes singular. And so it's no longer possible to invert it. And that's why this also doesn't exist in that case. Okay, so you see, it's important that all our variables, at least in the diagonal case, have variance which is not 0. Okay, so now suppose all these variances are non-zero. Then this exponent here gets a very nice shape. Do you see how the exponent then looks like? I mean, that's why I asked you to really look into this. Yeah? So take this vector formula and calculate one component, the ith component, and then you have to write down these multiplications as sums, and you really see what happens. And now if you apply this to such a diagonal covariance matrix, then your exponent finally is minus 1/2 times the sum over I equal 1 to d of sigma. So this is not a sum, it's the covariance matrix sigma inverse I times x I minus mu I. Okay? That's how the exponent then looks like. And now let's write the whole thing. So we get x of this. And now, I mean, this can be simplified very much. because now we have, oh, there is something missing. There is, of course, missing the square again here. Now we have the exponential function applied to a sum. And this can be written as the product of all the exponentials. The product of exp minus 1/2 sigma I inverse. Oh, sorry, yeah, this is, of course, that's how it has to be written. No, sorry. Sigma inverse, diagonal element, xi minus mu I squared. Yeah. So now what do we have here? I mean, here we have the product of d one-dimensional exponentials. Yeah? So we have the product of d one-dimensional normal distributions. Look, this is one-dimensional. Here we have, oh, danke. Here we have a scalar variable. This is just a number, II. Yeah? It's one element of the inverse matrix. So this is a one-dimensional Gaussian. So you see, if our covariance matrix is diagonal, then our multidimensional Gaussian comes down to the product of d one-dimensional Gaussians. Yeah, and I mean, this is just the basic fact that if our variables are independent, then p of x and y is equal to p of x times p of y. Look, these one-dimensional exponentials, these one-dimensional normal distributions are the densities of the individual one-dimensional variables. And if these variables are independent, that's when the covariance matrix is diagonal, then our multidimensional Gaussian splits up in such an easy product. Yeah. And I mean, what we see is that the mathematics of normal distributions is so nice because of this property of the exponential function, that the exponential of a sum is the product of all the exponentials. And that's basically one of the main reasons why we like the normal distribution so much. Because the math is so easy with it. With any other distribution, the math becomes much more difficult. But it's not the only reason. I mean, here we are really lucky in mathematics because normal distributions are important in many applications. And why are they so important? Because of the central limit theorem. Because whenever we have variables, when we have noise, when we have variables with noise, then quite often noise comes from a sum of random effects. And whenever we have a sum of random effects, And if these random effects are independent and identically distributed, then we can apply the central limit theorem, which tells us that in the limit for n towards infinity, any distribution becomes a normal distribution when we sum up these random effects. So whenever we have noise, we will now in the following make the assumption that it's Gaussian noise. And this assumption is not too bad, because whenever our noise is really random and independent, then the distribution, the noise distribution, is very close to a Gaussian distribution. So we are really lucky now, because Gaussian distributions are so important in statistics, and second, they can easily be treated mathematically due to this property. Yeah, and I mean there are more nice properties about the normal distributions and exponentials. We will see them. Okay, now let's look at these images here. So here, of course, in 2 dimensions, this is a normal distribution with the expected value in the origin. And here in these pictures, we assume a diagonal covariance matrix with variances equal to 1 in each direction. And now you see it's shifted to the right in x direction. This is shifted diagonally in x and y direction. And here you see, we saw it already, 3 different variances. And yeah, what's important is that, let's look at this. The variance in x and y direction is the same, and that's why the contour lines here are circles. As soon as the variances are not the same in both directions, we will get ellipses. Oh yeah. Do we have such an example? Let me see. No, sorry. Yeah, what we have here is, I mean, here you have a circle. If we would have, for example, 3 here in x direction and 1 here, then it would be an ellipse which is stretched in x direction. And now, here it's no longer diagonal. And that means our distribution will be turned around. So it will no longer be aligned in x or y direction. So here you see now it's exactly diagonal. Because, I mean, look, this covariance here tells us that x and y are no longer independent. Yeah? They are now we do have a positive correlation between x and y. And positive correlation means that typically data will be distributed along this diagonal. Yeah? If we have a negative correlation, we would have something like that. So with minus 0.5 here and here, it would be aligned in this direction. And if this covariance is bigger, then this means we have a stronger correlation of these 2 variables, and then it's stretched even more in this direction. So it gets more narrow in this direction, but longer in this direction. Okay, yeah, here you see negative correlation, and now it's stretched in this direction. Ah, yeah, okay, and here we have such an example with 2 different variances, and now you see in x direction the variance is larger than in y direction, but we also have a negative correlation, and that's why, so it's no longer exactly in this direction, it's a little bit shifted in this direction. or it's rotated in this direction, not shifted. Okay, yeah. Some properties of the covariance matrix. I mean, you see, we don't have the time to prove all this. Yeah? We will go towards applications. So I just state some of these examples. They are not really difficult to prove, but here we will just state them. The covariance matrix sigma is symmetric. Yeah? It is invertible, and it is invertible if no variances are 0. Yeah? So if we have a width going to 0, then it's not invertible. So under this assumption, it's invertible. And the inverse matrix is symmetric too. I mean, this holds for all symmetric matrices. All eigenvalues are real. This also holds for all symmetric matrices. All the eigenvectors are orthogonal. And the eigenvectors point in the direction of principal axis of the ellipsoid. I mean, that's what we actually have seen in PCA. And another nice property, the covariance matrix is positive definite. Positive definite means that this product x transpose sigma x is greater than 0 for all vectors x. All eigenvalues are positive, and the inverse is also positive definite. These are properties we will use. Okay, and now the covariance matrix, because it's symmetric and positive definite, it can always be diagonalized. I guess we had this last semester in the linear algebra, didn't we? I guess so. So any symmetric positive definite matrix can be diagonalized by a so-called principal axis transformation. And this is the transformation we have. Yeah? So let U1 through UD be the eigenvectors of this matrix sigma. Then there is a transformation from our original variables x to new variables y with this formula. So yi, the ith component of our new vector, is the ith eigenvector transposed multiplied with x minus mu. And this is a very important transformation, because if we apply this transformation, look, I mean, two things happen. First, we have a shift into one direction of our distribution. And you see what we get is we subtract the mu, the mean. Mu is the expected value of our Gaussian. So we subtract, first we subtract the expected value. And that means for such a case, we would just shift our distribution into the origin. That's the first step. We shift it into the origin, and then when we are in the origin, then what happens is we would rotate our distribution such that it becomes diagonal. And diagonal means that it's aligned parallel to the axis. Here it's diagonal, so this will no longer occur. And aligned parallel to the axis means, it's this case. it means the covariance matrix is diagonal. And this, and that's very important, this has the great advantage that in these new coordinates, which we have here in these new y coordinates, all variables are independent. They are independent, they are uncorrelated, and this means you can apply this factorization of the normal distribution. So the whole normal distribution factorizes into a product of one-dimensional distributions. Okay, yeah. Now some more results without proofs. There even is a way to even if the variables are dependent. That's the case. So we have such a normal distribution, so a first distribution with some expected value and a covariance matrix which is not diagonal. And another distribution with a different expected value and different covariance matrix. Then the product of these two distributions can be represented as a new normal distribution. I mean, and this is really a nice result. That's a very nice result. I mean, this is not true for arbitrary distributions. So if you have a binomial distribution and you multiply it with a different binomial distribution, this is not a new binomial distribution. But for normal distributions, this holds. Yeah. And I mean, there is one exercise, you really have to look at it. And you have to see it, and then yeah, suppose, let's draw a picture. Suppose we have one normal distribution with contour lines like that. And now suppose you have a second normal distribution that looks like this. And now let's for a moment do something simpler. We just take the sum of these two normal distributions, which is kind of the linear superposition. What is the sum? How does the sum of these two normal distributions look like? I mean, the two distributions, here we have this hill stretched along this direction and a second hill stretched along this direction. And now what is the sum of these two guys? How would it look like? That's what you have to do in your exercises. Yeah? So you take a plotting software and plot this guy, and then you plot the sum of these two guys. And you will see how it looks like. I mean, it will be a hill which goes like that, and here in the right angle it continues in this direction. And of course, such a hill with such a right angle here is by no means a normal distribution. So the sum of two normal distributions is not a normal distribution. But the product of two normal distributions is a normal distribution. How would the resulting normal distribution look like if you take the product of these two guys?
It's a peak where they overlap.
Yeah. It's quite a narrow peak, something like that. Yeah? And all this part here will vanish. Why? And this also will vanish. Why?
Because it's multiplied by 0.
Yeah. with almost 0. I mean, that's the property of the exponential function. It goes to 0 extremely fast. So this distribution at this point has a value extremely small. And I mean, this value is maybe 5. 5 times 10 power minus 25 is very small. Okay, yeah. So we can even multiply two arbitrary normal distributions with non-diagonal covariance matrices, and we get a new normal distribution. I mean, that's a really nice result. And there are even simple formulas for getting the new expected value and the new covariance matrix. This is the new covariance matrix. It's so simple. You take the two old covariance matrices and get the new one from this. And the new mean, that's how you get the new mean. I mean, proving this formula, this is not trivial because it's really technical going into look, I mean, yeah, we don't have it here, but with these vectors and matrices in the exponents and yeah. Okay, yeah, then next thing is marginalization. Did we? No, we didn't have this in the math lecture last semester, but we had it in AI. Yeah? So those who attended AI know what marginalization means. We did this with discrete variables. Now we have continuous variables. And marginalization is, it's nothing but projecting, suppose we have this distribution, it's nothing but projecting it onto a subspace. So if we have 2 dimensions, we may project it to the x dimension. That's what it's all about. And in the discrete case, we get the marginal distribution. Look, we have 2 variables x and y, or even 2 vectors x and y. And then we project it onto a subspace, onto x. And then what we did in the discrete case, we just took the sum over all the other variables. And here we take the integral over all the other variables. Okay, and now there again is a very nice formula for the normal distributions. So if we have such a normal distribution where the expected value is a vector consisting of this first, I mean this A is a vector and B also is a vector. And so it's a column vector where the upper part is A and the lower part is B. And the covariance matrix decomposes into such block matrices. And now if we want to project this normal distribution onto these first dimensions, then the marginal normal distribution is so simple. Look, it's just the normal distribution with this upper part of the expected value and with this sub-block matrix. It's so nice and easy. Okay, now we will also need conditional distributions. So we want to condition on some variables. So, and this is the conditional distribution, P of x given y. And it's defined as P of x and y divided by P of y. And again, there is a nice and easy formula for normal distributions. If this is our normal distribution and we want to condition y on x, then it's this normal distribution. with this expected value and this new covariance matrix. Okay, yeah, and now let's look at this picture. In this picture we see the difference between the marginal distribution and the conditional distribution. That's very important, and we will really need this. This is our original two-dimensional distribution. Yeah, and if we look at the marginal distribution, P of xa, so this is the dimension xa, and this is xb. And P of xa is this blue density function. Why is it? Now, look, project this distribution onto this axis. And what will you get? You will get exactly this. Is this clear? So it's just a projection. But now, if we take the conditional distribution, P of xa given xb equal to 0.7. Look, in a conditional distribution, we have to, in order to get a picture of the whole thing, we have to fix the second variable onto which we condition. So P of xa, given that xb is equal to 0.7, I mean, then what we get is a cross-section at this line. And this cross-section, of course, is a distribution which is much more narrow, with a standard deviation around this here. And that's why we get this red density function. Yeah. So it's easy to imagine what happens when we do marginalization. So marginalization means we just project onto a subspace, then we get something like that. But if we do conditioning, conditioning means we fix some variables at a fixed value, and then we get kind of a cross-section, and that's this. Yeah. And I mean, such conditional distributions will be quite important in the following. Because sometimes we will fix some parameters to fixed values, to given fixed values, and then that's what we get. Okay, yeah. Yeah, and I guess we should stop now. Thank you.